to Singapore was the fact that he's recently got married. So one thing that happens in India which doesn't happen in Singapore or any other country is that soon after you get married, you look more prosperous. You know what I'm saying? So the prosperity is India's speciality. But I'm sure many of us are convinced after your talk to pack bags and soon be in one of the greatest cities in the world, and that's Singapore. Thank you so much for that fantastic tour. Now let's move on to the next speaker, Mr. Paul Meinshausen, Chief Data Officer, PaySense, who specializes in machine learning and experimental methods for prediction, analysis, and causal inferences, and has a research background in behavioral and computational social science. Previously led data science at housing.com and Teradata International, Paul will take us through business learning for machines. Please welcome Paul on stage.
Seems my file format wasn't being friendly with the laptop. Great. So I want to talk today about a concept that I think a lot of you probably have heard about, machine learning. But I want to take a slightly different approach than maybe you typically hear. A lot of times when people talk about machine learning, they talk about it from the perspective of the code and the analytics and what the problem being solved is. And I want to take the perspective of what an organization and how people learn within an organization and a business to act and interact with their machines in a way that can allow them to learn. Okay, before I do that, I'll just give you a little background on myself. As the very warm introduction said, my background is actually in computational social science and cognitive science. So when I did my graduate research, I was looking at less in technology and more at humans and how people make decisions within social contexts. So I did work in running large-scale psychology experiments. And after grad school, I went to work for a couple of years for the Department of Defense, the US Army, and I was working on looking at doing machine learning and analytics for problems like irregular warfare in places like Afghanistan and Iraq. After that, I went back to academia for a while and spent some time, another 2 years doing more experimental research at Harvard University, where we ran large web experiments, interacting with people online. After that, I moved to Singapore, which is a very lovely place. I can assure you. And I was lead for data science for Asia. For Teradata, which is a large analytics data company. And then I moved to Mumbai, which is also an excellent city. I've been here for a few years. And I was vice president of data science at housing.com. And now I'm a co-founder and chief data officer for a financial technology startup called PaySense. And I'll talk a little bit as I go through some real, I hope, interesting examples from some of the work I've done that will illustrate some of the points, and I hope that'll help keep it a little lively and interesting for you. Okay, so just start with just a little bit of an introduction. So what is machine learning? So machine learning, just very simply, is computer science where the problem you're solving is solved to some degree by the computer itself. If you want some job to be done, you're not explicitly programming the computer to do that job, but you're allowing the computer to learn how to do it on its own. Okay, but to actually do machine learning, it's not just about the code, like I said before. Code that does machine learning emerges from an organizational context that allowed the machine to learn. So what do I mean by that? Well, let's get a little more specific about what it means for a machine to learn. Okay, so there's a famous definition that if you'll just get technical with me for just a minute, that'll help us think very concretely about what we're talking about here. A famous definition, I think it's even quoted on Wikipedia, is a computer program is said to learn from experience E, okay, with respect to some class of tasks T, and performance measure P, if its performance at task T as measured by P improves with experience E. Okay, that's a little crazy. So that's, okay. the keys there you want to pay attention are to experience, E, tasks, and your performance measure. Okay, and we're going to give some good examples of those. Let me just close this because it's getting in the way. Okay. All right, so the thing is, as you're trying to develop machine learning in a context, in your context, for your organization, the thing you're asking, and the problem that becomes quite difficult, and I think frustrates most organizations when they're trying to set this capacities up, how do we get our artificial intelligence, how do we get our machines to solve problems with us and for us, is asking these questions, which T? So what tasks are suitable for machine learning? And which P? What's the right performance measure? How do we know that this is getting better over time? And what does it mean to be better over time? And then which E? Because it improves with experience E. And that's something really important. Machine learning is a repeatable endeavor. It happens over and over and over again. And by happening over and over and over again is how you actually improve. Okay, I'll just give a kind of a break here, okay? Another thing, machine learning is often coupled with data science. And most times when people think of data science, they're thinking of Star Trek like data. And this is data science. This is a guy who just knows everything and you ask him whatever and he has an answer for you. You don't really understand how he came up with that answer. It's just an answer, right? That's fine, but that's still science fiction. What I like to think about is data science. So it's the science part that's really important. And what is science? It's a replicable, reproducible process of asking questions that can be proven false or can be that we can be skeptical about, accumulating evidence, evaluating that evidence, and then coming to a decision or an inference about the question you asked. Okay, so let's start with an example. All right. So during this one I think illustrates remember the questions. Which T? Which tasks are we going to solve? Which performance measures? Okay, so during World War II, the U.S. Department of the Army, same one I worked for, set up a group called the Statistical Research Group that worked in New York City. And this was just a bunch of mathematicians and statisticians. And while the troops and the army was off fighting a war, they would sit in their office and try and think hard about problems and solve them. And one such problem that the Air Force came up with was the problem of their planes getting shot down. So the planes would go off to bomb German forces in Europe, and they'd come back shot up, and we would lose planes and we would lose men, and this was a big problem. So the Air Force said, okay, we need to figure out how to solve this, and solving it is an optimization problem. So if you have planes and you want them to not be shot down, you add armor to them, right? But if you add too much armor to them, they get heavy and they can't fly as far. And they use more fuel, so it's more expensive. So what you have to optimize is how much armor to add so that they don't get shot down without adding too much so that you can't go anywhere. Because they have to fly all the way from Britain into Germany. Okay, so the Army said, oh, here's some data we have to answer this problem. And this is all the planes that have come back. And here's where all the bullet holes were in the planes. And so, look, now you can figure out where all the bullets are, and that's where you can put all the armor, and you just have to tell us how much armor we should put in there. What's the right optimization? Okay, and there was and the group kind of said, oh, they looked at the data for a bit, and they looked at the question for a bit, and they said, you know what, I think you should actually be putting the armor, and this was a breakdown of where the bullet holes were. So it's covered up here, but this one at the top is the engine, and then this is the fuel system. It's receiving about 1.73 bullets per square foot, and this is that's the fuselage, and then the fuel system is receiving about 1.5 bullets, and the rest of the plane about 1.8 bullets per square foot. Okay, so they said, okay, so this is where you should put your armor. Okay. This is where the Air Force thought they'd put their armor. But this discovery said, you know what? I think you need to put your armor where the bullets aren't. Okay. Why did they come to that conclusion? It turns out that the assumption the military was making was that that the planes that came back are representative of all their planes. Okay, and so this is where the bullets are getting hit. So you should, put your armor there, right? But the planes they brought weren't representative of all the planes, right? They weren't representative of the planes that don't come back. Okay, the planes that don't come back get the bullets where you never see. Okay, and that's where you need your armor, because where they come back with bullets, those bullets don't seem to bring the plane down, right? It's the bullets that bring the planes down that never come back. Those are the ones you're worried about. So you should be putting your armor up where the engines are. Okay. So what this illustrates is that you have to be asking what your question is. It's a lot of times. My professor used to always use this quote from a famous statistician, Ronald Fisher. To consult a statistician after an experiment is finished or a product is developed is often merely to ask him or her to conduct a post-mortem examination. Okay. So machine learning, to be done well, when an organization does it well, it's not just about saying, oh, here's the business problem, here's the question, now you come up with the solution. It's about asking, what's the right question in the first place? What problem is the one we want to solve? And what's the missing data? What are the key assumptions we're making? Okay. All right, so now you've figured out your right question. You've figured out the one that is worth asking and the one that's going to help you. And then there's this quote I like a lot, and it says, if you have a tough question that you can't answer, and you usually can't, if it's interesting, you can't answer it, right? Then first tackle a simpler question that you can't answer. So now you've got your question, and what you do is you begin to break it down. And you say, I've got a problem space here, but I'm not going to tackle the problem space I started with. I'm going to break it into its constituent parts. And you solve as small a piece as possible, and then you build it back up. So when you're deciding how does my machine gonna perform some task and be measured against performance P, right? It should be measuring against the performance at the smallest piece possible. Okay, what does that mean? All right, so I'll give an example from housing.com. So I don't know how many people here are familiar with housing.com, but just an update. It's an online real estate platform where you can search for used to be rent and buying houses. Okay, and at housing, we listed out houses and apartments and allowed people to connect. And one of the things we did in order to know when people would call a listing, call a broker or an owner, was we would provide a contact number. Okay, but instead of just providing a contact number, we would actually provide the actual contact number. We would provide a masked number. So what that means is we would rent this number from another service provider. They would give that to us. We would put that on there. And when you dial that number, it gets rerouted to the number of the broker. And what that allows us to do is actually see when the call is being made. So if we just list some broker's number and it's called, we would never know, right? So that's the data we would never see. So we make an investment and we mask, and now we see the calls. Okay. That's great. It's really helpful. Gives us a lot of data. But at housing, when I was there, we were adding around 4,000 properties a day, and masking all of them gets quickly very, very expensive, and not really feasible from a business perspective. So they all need to be masked. But how can we do it efficiently? So one of the questions we would ask is, how long before we can remove a mask? How long before the number is not getting any calls, right? And that's your trade-off here. Is you want to keep the mask on long enough to get all the calls to that number, but not a day longer to spend for masking when you don't get a call, right? And you don't want to, so if you did it either way, on either extreme, you could put the mask on for one day and take it off, and then you'd miss a whole lot of calls. Or you could leave it on for 100 days and be super sure you're not missing any calls, but you'd be spending a lot of extra money. So what's the optimum, how do you balance, what's the right amount before you demask? So we looked at all kinds of data, and this part we'll talk about it in a little bit as well, but we looked at things like across a day, when are calls being made? So that we would know, for instance, if a call drops off, it might just be because people don't tend to call early in the morning. All kinds of, and came up with a pretty good solution for demasking calls. Okay, and we're getting this request from our business operations, right? The team that's actually paying this money and has these resources that they need to save. Okay, at the same time, we've got a different set of problem. And that problem is our users. And our product team cares about a different problem. And they have the problem where we've got a user and users who, they need to find a new apartment. So they say, oh, the weekend's coming up, and I'm going to spend some time and I'm going to find my new house. Okay? But a terrible experience is when